All right, back when you were in geometry, way back, you learned the definition of part of a circle. We call part of a circle a sector, and the definition of the area is 1/2 r squared theta. Okay? So if you were doing the full circle, what would you put in for theta?
2 pi.
You'd put in 2 pi. So if you were doing the full circle, it would be 1/2 r squared times 2 pi. What do you get for that? Pi r squared, which is the formula for a full circle. Okay, when you're only doing a wedge or a portion, it's 1/2 r squared, whatever theta happens to be, however much of theta it is. So if theta was 90 degrees, or if theta was pi fourths, then that would give you a quarter circle. Okay, I just need you to tuck this little bit back into your head, okay? Okay, polar coordinate area is measured differently than rectangular area. Go ahead and put a y-axis that cuts right down this way, and put a horizontal axis that goes right through. If we were in rectangular coordinates, we measure the area this way. All right, we go from left to right for rectangular coordinates. Polar doesn't work that way at all. Okay, in polar, everything emanates from the origin. So you can just go ahead and erase everything you just did. Put the axes back. In polar, we measure everything from the origin like this, out in almost like a fan. It's fanning out. And we divide this into, okay, rectangular, we were doing rectangles, and we were doing all rectangles, or trapezoids, we were doing all different shapes. In polar, everything are sectors. Okay, the more sectors you have, the better area you have. So it's all sectors. Okay. Ideally, these sectors are sliver thin. Okay, they're super tiny. So what we're doing is we're taking one sector. So remember, one sector is 1/2 r squared theta. That's one sector. We're adding up all the sectors, so we use sigma. The number of sectors we have starts with the first sector, and we go to the last sector. And ideally, how many sectors do we have in an ideal world? Infinite. So we indicate that as the limit as n approaches infinity. And what is driving this is that the theta is changing. The theta changes as you swing through this thing, and so we have delta theta out here. That's what's changing. It's the theta that's driving it. In calculus, what do we replace this whole symbol with? An integral, okay? The limit of the sigma summa notation is an integral. And so for us to find the area, we are going to do the integral of 1/2 r squared theta d theta. All right. Let me just here are some other pictures. So you can see how everything emanates from the origin and swings out around. You're going to bound your area by your theta. Your theta will control where you start and where you stop. If your theta is 0 to 2 pi, then that means you're going to do the full swing all the way around. If your theta is smaller than that, then you'll never go more than 2 pi. Okay, 2 pi would be the most. If your theta is, then you're only going to do a section of whatever quadrant you're going to end up in. All right, so here we go. The area for the region between the origin and the curve from alpha to beta is, and so now we're going to define it as the integral, whoops, I want red, from alpha to beta of 1/2 r squared theta d theta. Okay, because it's the theta that's swinging from alpha to beta. The trickiest part is finding the bounds. The bounds alpha and beta, if they're not given. If they're given, easy peasy, you've got the bounds. If they're not given, that can be the trickiest part. If you pick the wrong bounds, you're going to be finding the wrong section of your polar graph, or you're going to overlap maybe, and you're going to count area double. So you want to make sure that you're finding the right boundaries. And I'll show you how to do that both with and without your calculator. All right, so find the area of the region in the plane fully enclosed. All right, well, if it says fully enclosed, then you know that your bounds are 0 to 2 pi, because we're doing the full thing. So this would be set up this way. 0 to 2 pi, 1/2, the radius squared, and in this situation, the radius squared is 2 quantity 1 plus cos theta, quantity squared, so that whole thing squared. D theta. Did I write it wrong on the others? Yeah. This theta is not there. Because the theta is so small, it's a d theta. That's the theta that's changing, I'm sorry. And then you just let your calculator do the work. If you're in radian mode, or polar mode and radian mode, you're just gonna do a math 9, and you're gonna just evaluate that, all right? So let me pause a minute. Yeah, so one thing you might wanna consider is taking this and pulling it out to the front and having your 1/2 be outside. That should be 9.425. Okay, let's try another one. All right, this is a fun one to draw. Go ahead and draw this with a full 0 to 2 pi, just for starters, just to get a look at what it looks like. Your window should be fine to be like negative, it can be small. It could be like -3 to 3, it doesn't need to be super big. All right, so we end up with, as you watched it draw, it was like going like this, and then like this, and then coming back again. Okay, we just want the area of the inner loop. Okay, we just want the area of the inner loop. Okay, so when is that inner loop getting created? Well, when it forms the inner loop, what's the distance from the origin? Like 0, right? The boundaries are going to be set every time this thing crosses 0. Now, it crossed 0 several times. Go ahead and sometimes it's easier to watch it. Go back to your y equals, and on the very, very far left, using your enter key, you can change it to be the little, I like the little thing with the ball head on it, and I watch the graph that way, and I see how it draws. Okay, so we need our boundaries. So we need 2 cos theta plus 1 to be set equal to 0 to find our bounds, because 0 would be every time it crossed the origin. So that'll be cos theta being equal to -1/2, and that happens multiple times. Okay, cos theta is equal to -1/2. Every time cosine crosses it, it gets to a certain radian level. What's the first radian where cosine would be equal to -1/2? If cosine is the x coordinate or whatever, as you're thinking about that.
4 times x.
I think it happens before that. Doesn't it happen in quadrant 2?
Yeah, isn't that 2 by 30?
Oh, sorry, 2, yeah, okay. 2 pi thirds is the first time. When else does it happen again? Four pi thirds, okay? So it happens 2 pi thirds and 4 pi thirds. Okay, try shrinking your window, your bounds to those values. Okay, so 2 pi thirds and 4 pi thirds. Okay, did that just give you the little inner loop? And that's what we want. So we want this inner loop. Okay, so now we know our bounds. That's the trickiest part. Now you just have to set up your, I'll put my 1/2 on the outside. My bounds are going to go from 2/3 pi to 4/3 pi. And the radius is going to be squared. So 2 cos theta plus 1 quantity squared d theta. So once you have your bounds, then finding the area should be no problem. Okay, you don't need to practice that again. I know you know how to type in an Math 9. Okay, same shape. How do you find the area inside the outer loop, but outside the inner loop? Inside the outer loop, but outside the inner loop. So do you understand what I'm asking? Okay, so it's this. Okay, and I want this, all this area. Okay, so yeah, I got to do the whole thing minus that little bit that I just found on the one before. Okay, so the whole thing is going to be 0 to 2 pi. But then I want to take away the little bit from the 2/3 pi to 4/3 pi. So you'll set that up as 1/2 0 to 2 pi of the radius 2 cos theta plus 1 quantity squared d theta, and then minus the other one. Okay, so that's how you're going to set that up as subtraction. Yeah.
So for finding the inner loop, is it just a given to set r equals 0 to find
Yeah, because the loops are going to be whenever it's crossed through the origin, which is why that's why we set it equal to 0, because it's crossing through the origin. Now, if we're going to do 2 graphs on top of each other, we want to find the intersections, then we set them equal to each other to find the bounds. But this one was finding it when it was crossing the origin. Okay, here's a pretty one. Find the area of the 6 petaled rows. R squared equals 2 sine 3 theta. What's the inherent problem with graphing this with your calculator? It's r squared. So how are we going to graph that correctly? So you're going to have to put 2 in. In your one of them, you're going to have R1. R1 would be the positive 2 sine 3 theta, which is going to give you half the petals. And then your R2 would be the negative square root of 2 sine 3 theta. Okay. But if it's a 6 petaled rose and all the petals are equal, what do you really just need to find? One petal. Okay, 1 petal would be fine. All right, so if you take a look at that picture, if you go 0 to 2 pi, you'll see all the petals. And if you limit your bounds, you'll see only some of the petals. All right, so I'm going to do mine. 2 sine 3 theta and negative 2. Oops. I like to start with 0 to 2 pi. I just like to be able to see the whole thing. Mine is in different colors, my petals. window right now is going negative 10 to 10.
Yeah.
So make your X and Y smaller, yeah, or you could zoom in, that would also be another way. All right, so we only need to really focus on one of the petals, because we don't need to do all 6, we can just find one of them, and then hopefully remember to multiply by 6. So let's find the bounds just for one petal. So to find the bounds for one petal, I take one of the equations and I set it equal to 0, so I'll just take 2 sine 3 theta and set it equal to 0, and I square both sides, still have 0. Divide by 2, still have 0. And when sine of 3 theta is equal to 0, that happens at 0, pi, 2 pi, 3 pi, 4 pi, etc. But that's equal to 3 theta. A single theta would be 0 pi thirds, 2 pi thirds, 3 pi thirds, etc. So a single petal should be going from maybe 0 to pi thirds. So then check it though, okay? Check what you get. If you change it to 0 to pi thirds on your window, you should get one petal. Now, mine doesn't look like it's closed all the way. Does yours? Okay. And that doesn't quite look like it's getting all the way. That's only because my my change in my theta is, I used pi, I think I used pi over 32. If you make it smaller, it'll give you more of a closure. But you've seen that sometimes on your graphing calculator before, like it's supposed to be a semicircle and it doesn't quite touch. Okay, it is a closed circle. All right, so we're going to take this one petal, so it'll be 1/2 of 0 to pi thirds of r squared, which is 2 sine 3 theta d theta. That's one petal. And then I need to make sure I multiply that by 6 to get my total area. I always recommend checking the visual to make sure that your bounds aren't giving you something you don't think that you actually want. All right, this is the last one. Okay, how do you do it if you have two different polar shapes on top of each other or intersecting each other and you're trying to find the area between them? So not between it and itself, like one loop and itself, but how you do it between two different ones. Well, you just use subtraction, but you have to find your bounds by setting them equal to each other. Sorry, I gave you 24 as a duplicate slide. You can go back to this one. Okay, so here we have two shapes, a circle of radius 1 and a cardioid of r minus cos theta. All right, so put both of these into your, put one into y1 or r1 and one into r2. So one is expected to be a circle, one is expected to be a cardioid, which I call a lima bean. To me, it looks like that. Take a look at 0 to 2 pi as your window to get an idea of what the whole thing looks like first. You should have a circle of radius 1, and then you should have a cardioid like that. Okay, we want this to be inside the circle, but outside the cardioid. So we should be looking at this area right here. It's in the circle, but not in the cardioid. So we want to find out, I didn't draw my drawing, shoot, very good. It should have intersected. I tried, it should have intersected more like that. Try to fix that a little bit. Okay, so we want to find the intersection points by setting these two things equal to each other. And so we would have 1 equal to 1 minus cos theta. And then we would solve that mathematically. So 0 equals negative cos theta. So theta is every time the cosine is 0, which happens at negative pi halves. It happens at positive pi halves. It happens at 3 pi halves. Okay, all of these values. Even just looking at the quadrants we have, we want to do negative pi halves, which is the fourth quadrant, up through positive pi halves, which is the first quadrant. So we want to cover all that area. But we have to set it up as a subtraction. So I'm going to go from negative pi halves to positive pi halves. Put my 1/2 out front. And I want to use the outer edge, and the outer edge has to come first. So this is what's considered the outside edge, the circle. So that would be 1 squared d theta. And then I want to subtract from that the same bounds for what's forming the inner edge, which is 1 minus cos theta squared d theta. So that's the setup. So they both have 1/2. So you could save your 1/2 till you were done. You do the subtraction of the math 9s, and then the subtraction of the inner parts that you want to take away. .214. All right, we're just going to set up this last one. Find the area shared by these two circles. So one of them is radius 2 and one of them is radius 4 sine theta. So you can take a look at those two things. So of course we know what radius 2 looks like. So I've got one of mine that's coming around like this with radius 2. And then my other one, the 4 sine theta, looks like this. Okay. And so we want the area shared by these. So we want the area bounded in between here. So in that boundary, the outer edge of that boundary is following what for me is my blue line. And then I want the intersection points of where those two things intersect. So I set them equal to each other. So 2 equals 4 sine theta. So 1/2 equals sine theta. And I know all the places where sine theta equals 1/2. Okay, the first time that sine theta equals 1/2 is pi sixths. The next time that theta equals pi halves is 5 pi 6. So my boundaries are pi 6 to 5 pi 6. So I'm going to do the outer minus the inner. So 1/2 of the boundaries pi 6 to 5 pi 6. And then my outer edge is formed by 2 quantity squared, and then minus the inner one. And its inner edge is formed by 4 sine theta quantity squared d theta. And then you'll subtract that to get those two. Yeah.
So is the outer edge typically like the top?
The one that's farthest away from the origin. Okay, because everything's measured from the origin, so the outer would be whichever one's farthest away from the origin. Yeah, so don't think top and don't think sides, but think farther away from the origin.